Right now, as you're watching this video, something extraordinary is happening that defies every intuition you have about reality. The total energy content of the entire universe, every star, every planet, every particle, every photon of light, every quantum field fluctuation across 93 billion light-years of observable space might be exactly zero. Not nearly zero, not approximately zero, but precisely, mathematically, perfectly zero. We've been taught to think of energy as something substantial, something that accumulates and grows. When you charge your phone, you're adding energy. When you eat food, you're consuming energy. When stars burn nuclear fuel, they're converting mass into energy. The universe seems to be an enormous reservoir of positive energy, constantly creating more through stellar fusion, cosmic expansion, and countless other processes. But here is what makes this deeply unsettling. For every joule of positive energy that exists in the cosmos, there appears to be an exactly corresponding joule of negative energy that cancels it out completely. The universe isn't just balanced in its energy content. It is so perfectly balanced that the cosmic energy ledger reads exactly zero, as if reality itself is an elaborate accounting trick where enormous positive and negative quantities cancel each other out with mathematical precision. This isn't just an abstract physics concept with no real-world implications. The mechanism by which the universe balances positive and negative energy is what allows everything you see around you to exist. Without this perfect energetic equilibrium, matter couldn't form, space couldn't expand, time couldn't flow, and conscious beings like yourself couldn't emerge to contemplate these mysteries. For over a century, physicists have been uncovering the hidden mechanics of cosmic energy balance, and what they've discovered challenges our most basic assumptions about the nature of existence itself. The universe operates like a cosmic bank that can create infinite wealth as long as its books always balance to zero. Every star that shines, every galaxy that forms, every thought that emerges in your brain represents a transaction in this cosmic accounting system where positive and negative energy must always equal out. The story begins with Albert Einstein's realization that mass and energy are interchangeable through his famous equation, E=mc. But Einstein's insight was just the beginning. Modern physics has revealed that the universe contains forms of energy so exotic and counterintuitive that they challenge the very concept of what energy means. There's gravitational potential energy that's negative by definition, quantum vacuum energy that fluctuates between positive and negative states, and dark energy that appears to violate energy conservation while somehow maintaining cosmic balance. Tonight, we read diving deep into one of the most profound questions in all of science. How does the universe maintain perfect energy balance while creating the apparent abundance of matter, energy, and structure we observe? We'll discover how negative energy isn't just a mathematical abstraction, but a physical reality that shapes everything from the quantum vacuum to the expansion of space itself. We'll explore how this energy balance enabled the Big Bang to create everything from nothing, and why this cosmic equilibrium might be the key to understanding why anything exists at all. 3 revelations await you that will forever change how you understand the nature of reality. First, you'll discover that gravity isn't just a force that pulls objects together. It has a cosmic debt collection system that ensures every bit of positive mass energy in the universe is balanced by an exactly corresponding amount of negative gravitational energy. The more massive objects become, the deeper into energetic debt they fall, maintaining perfect balance even as they grow more powerful. Second, you'll learn that the quantum vacuum, the supposedly empty space between particles, is actually a seething cauldron of positive and negative energy that constantly borrows from and repays itself through virtual particle creation and annihilation. These quantum fluctuations don't just maintain energy balance. They re what prevents the universe from collapsing into perfect nothingness and what drives the expansion of space itself. Third, and most mind-bending of all, you'll realize that consciousness itself might be the universe's most sophisticated energy balancing mechanism. Your brain processes information by creating and destroying energy patterns in ways that maintain local thermodynamic equilibrium while participating in the cosmic energy balance. Every thought you think, every memory you form, every decision you make represents a microscopic transaction in the universe's energy accounting system. The implications are staggering. If the universe maintains perfect energy balance, then the Big Bang did not create energy from nothing. It borrowed infinite positive energy from the vacuum while simultaneously creating infinite negative energy through gravitational potential. The cosmic expansion we observe isn't adding energy to the universe. It's redistributing existing energy between positive and negative accounts while maintaining zero net balance. This investigation will take us from the subatomic realm, where virtual particles dance in and out of existence, to the cosmic scale where dark energy drives galactic recession, to the event horizons of black holes where the very definitions of positive and negative energy break down. We'll explore how this energy balance explains the fine-tuning of physical constants, the arrow of time, and the emergence of complexity in what should be a perfectly symmetrical universe. Recent discoveries in cosmology have revealed that this energy balance is even more precise and more mysterious than physicists initially imagined. The Planck satellite's measurements of the cosmic microwave background show that the universe's total energy density is flat to within 1 part in 1,000, and precision so exact that it suggests the energy balance isn't just approximately zero, but mathematically perfect. But this precision creates its own puzzles. How does the universe maintain such perfect energy balance across billions of light years and billions of years of evolution? What mechanisms ensure that every positive energy creation is matched by negative energy creation? And why does this balance produce a cosmos filled with structure and complexity rather than remaining in perfect, empty equilibrium? If you're fascinated by the hidden mechanics that govern reality and want to understand how the universe performs the ultimate balancing act, subscribe and hit the thumbs up button. And here is a question that might fundamentally change how you think about existence. If the total energy of the universe is zero, what does that tell us about the relationship between something and nothing? Comment below with your thoughts. I'll pin the most mind-expanding response. The cosmic energy balance we're about to explore isn't just an interesting aspect of physics. It's the fundamental mechanism that makes existence possible. Every star that burns, every planet that forms, every life form that evolves, and every conscious moment you experience exists because the universe has discovered how to create infinite abundance while maintaining perfect equilibrium. As we embark on this journey through the cosmos's accounting department, remember that you're not just learning about abstract physical principles. You're rediscovering the deepest mechanisms of reality itself, the cosmic bookkeeping that allows something to emerge from nothing while ensuring that the universal ledger always balances perfectly. Now let's begin our exploration of how the universe balances positive and negative energy, and why this balance might be the most important fact about reality itself. Chapter 1. Perfect Balance in 1915. A young patent clerk turned physicist named Albert Einstein sat in his apartment in Berlin, struggling with equations that would revolutionize humanity's understanding of energy, mass, and the very fabric of space-time. What Einstein discovered would eventually lead to one of the most startling conclusions in all of science. The total energy content of the universe might be exactly zero, maintained in perfect balance through mechanisms so elegant and precise that they suggest reality itself operates according to cosmic accounting principles. Einstein's field equations revealed that energy and mass curve the geometry of space-time, creating what we experience as gravity. But hidden within these equations was a profound insight about energy conservation that wouldn't be fully appreciated until decades later. The gravitational field itself carries energy, negative energy that exactly balances the positive energy contained in matter and radiation. Every star, every planet, every particle in the universe exists in a state of perfect energetic equilibrium. To understand how radical this concept truly is, consider what we mean by positive and negative energy in physics. Positive energy is what you're familiar with, the energy stored in chemical bonds, the kinetic energy of moving objects, the mass energy locked inside atomic nuclei, the electromagnetic radiation streaming from stars. This is the energy that powers your body, lights your room, and drives every process you can directly observe. Negative energy, by contrast, is more subtle and counterintuitive. It is not the absence of energy, but rather energy with the opposite side, energy that can cancel out positive energy when the two are combined. In gravitational systems, negative energy emerges from the fact that it takes positive energy to separate gravitationally bound objects. The energy required to completely separate all the matter in the universe and spread it infinitely apart turns out to be exactly equal to all the positive mass energy that exists. The mathematics is surprisingly straightforward once you grasp the underlying principle. When you lift an object against Earth's gravity, you're adding positive energy to the object Earth system. But from the perspective of the gravitational field, you're actually making the system less bound, which corresponds to adding negative gravitational potential energy. The total energy of the system remains constant, positive kinetic and potential energy balanced by negative gravitational binding energy. Scale this up to cosmic proportions, and you encounter what physicists call the zero-energy universe hypothesis. According to this proposal, first articulated by physicist Edward Tryon in 1973, the total energy of the universe, including all matter, all radiation, all fields, and all gravitational potential energy, sums to exactly zero. The cosmos is not an enormous reservoir of positive energy, but rather a perfectly balanced system where positive and negative energies cancel out completely. The evidence supporting this hypothesis comes from multiple independent lines of investigation. Cosmological observations of the universe's geometry show that space is remarkably flat. The cosmic microwave background radiation reveals curvature parameters consistent with a universe whose total energy density equals exactly the critical density required for zero total energy. The Planck satellite's precision measurements place the universe's flatness parameter within 1 part in 1,000 of perfect flatness. But the zero-energy hypothesis raises profound questions about the nature of existence itself. If the universe's total energy is zero, how can it contain so much apparent abundance? Trillions of galaxies, each containing billions of stars, vast quantities of matter and radiation distributed across unimaginable volumes of space. The answer lies in understanding energy balance not as a static equilibrium, but as a dynamic process of continuous creation and cancellation. Think of the universe as a cosmic bank that operates under extremely strict accounting rules. The bank can create unlimited amounts of wealth, lending out positive energy to create matter and radiation, as long as it simultaneously creates exactly corresponding amounts of debt in the form of negative gravitational potential energy. Every star that forms, every galaxy that assembles, every structure that emerges in the cosmos represents a transaction in this cosmic banking system where the books must always balance to zero. The Big Bang itself represents the ultimate example of this cosmic accounting. Rather than creating energy from nothing, which would violate conservation laws, the Big Bang created equal amounts of positive and negative energy simultaneously. The rapid expansion of space borrowed infinite positive energy from the quantum vacuum, while simultaneously creating infinite negative energy through gravitational potential. The net result was a universe that began with zero total energy and maintained zero total energy throughout its evolution. This perspective transforms our understanding of cosmic evolution from a story of energy expenditure to a story of energy redistribution. When stars burn nuclear fuel, They not destroying energy, but rather converting mass energy into radiation while slightly reducing the gravitational binding energy of the stellar system. When galaxies form through gravitational collapse, they're not creating energy, but rather converting positive kinetic energy into negative gravitational potential energy. The precision required for this energy balance is extraordinary. Computer simulations of cosmic evolution show that if the positive and negative energy components were even slightly unbalanced, the universe would either collapse back on itself within microseconds or expand so rapidly that no structures could ever form. The perfect energy balance we observe appears to be fine-tuned to within 1 part in 1060, a precision so extreme that it suggests fundamental principles of physics we don't yet fully understand. Recent developments in quantum cosmology have provided new insights into how this energy balance might be maintained dynamically. The concept of eternal inflation suggests that the universe continuously creates new regions of space, each with its own energy budget that must balance to zero. This inflationary process doesn't violate energy conservation because the creation of positive mass energy is always accompanied by the creation of negative gravitational potential energy. The Wheeler-DeWitt equation, sometimes called the Schrödinger equation for the universe, provides a quantum mechanical description of cosmic evolution that naturally incorporates energy conservation constraints. Solutions to this equation suggest that universes with non-zero total energy are unstable and decay rapidly, while universes with exactly zero total energy can persist indefinitely and evolve complex structures. But the zero-energy hypothesis has implications that extend far beyond cosmology into quantum mechanics and thermodynamics. If the universe maintains perfect energy balance at cosmic scales, then similar balance principles might operate at every scale from the subatomic to the galactic. This could explain why quantum field theories require careful renormalization procedures to eliminate infinite energy divergences. The infinities might be artifacts of failing to properly account for the positive-negative energy balance. The anthropic principle provides another lens through which to view cosmic energy balance. Among all possible universes with different energy balances, only those with perfect zero energy can evolve the complex structures necessary for life and consciousness. We observe a perfectly balanced universe not because of lucky cosmic coincidences, but because only perfectly balanced universes can support observers capable of making the observation. Dark energy and dark matter, which together comprise 95% of the cosmic energy budget, play crucial roles in maintaining universal energy balance. Dark energy provides the positive energy density that drives cosmic acceleration, while dark matter's gravitational effects contribute negative potential energy. The precise ratio between these components appears to be fine-tuned to maintain perfect energy balance while allowing structure formation. The study of black holes has revealed additional complexities in cosmic energy accounting. Hawking radiation appears to carry away positive energy from black holes, but the holographic principle suggests that this energy is balanced by negative energy contributions from the black hole's interior geometry. The information paradox in black hole physics might be fundamentally related to the requirement that energy balance be maintained, even in the most extreme gravitational environments. Consciousness itself might play a role in cosmic energy balance through its relationship with information processing and thermodynamic irreversibility. The formation of memories, the processing of sensory information, and the generation of thoughts all involve energy transformations that must respect conservation laws. Your brain operates as a sophisticated energy balancing mechanism that maintains local thermodynamic equilibrium while participating in larger cosmic energy flows. The perfect balance of positive and negative energy thus reveals itself as perhaps the most fundamental organizing principle of physical reality. This balance doesn't just allow the universe to exist. It determines how structures can form, how evolution can proceed, and how consciousness can emerge. Every aspect of cosmic evolution from the first moments after the Big Bang to the formation of galaxies to the development of life, represents variations on the theme of perfect energy balance maintained through dynamic redistribution between positive and negative components. Understanding cosmic energy balance provides crucial insights into why the universe exhibits the particular features we observe rather than remaining in featureless equilibrium. Perfect energy balance doesn't require perfect symmetry or uniform distribution. It allows for the creation of complex structures and energy gradients as long as the total energy budget remains at zero. This balance between constraint and freedom, between conservation and creativity, might be the key to understanding why reality is interesting rather than trivial. Chapter 2. Gravitational Debt in the Basement of Stanford University Physicist. Leonard Susskind stands before a whiteboard covered in equations that describe something almost impossible to visualize. Gravitational potential energy so negative that it exactly cancels out all the positive mass energy in the observable universe. As Susskind explains to his graduate students, gravity isn't just a force that pulls objects together. It's the universe's debt collection system, ensuring that every bit of positive energy that exists is balanced by a corresponding amount of negative gravitational energy. This concept revolutionizes how we understand mass, energy, and the very existence of structure in the cosmos. When you hold a rock above your head, classical physics tells you that the rock possesses gravitational potential energy relative to the ground. But the deeper truth is more startling. The rock-Earth system has actually become more negatively bound, accumulating gravitational debt that must be repaid if the rock and Earth are ever to be completely separated. To grasp why gravitational energy is negative, consider what it means to completely unbind a gravitational system. Imagine trying to separate every atom in your body and scatter them to infinite distances apart. The energy required for this process would be enormous. You'd need to overcome the gravitational attraction between every pair of particles. This binding energy represents the gravitational debt that your body carries simply by existing as a coherent mass. The mathematics of gravitational binding energy reveals why this debt grows as systems become more massive. For a spherical mass m with radius r, the total gravitational binding energy scales as gm squared r. The negative sign isn't just a mathematical convention. It reflects the physical fact that gravitational binding reduces the total energy content of a system. The more massive an object becomes, the deeper its gravitational debt grows. This relationship has profound implications for cosmic evolution. When the first stars formed from collapsing gas clouds, they weren't just creating positive mass energy through nuclear fusion. They were also accumulating enormous gravitational debts as their material became more tightly bound. Every stellar formation event represented a cosmic transaction where positive nuclear energy was balanced by negative gravitational potential energy. The Sun provides a concrete example of how gravitational debt operates in practice. Our star contains approximately 2 kilograms of matter, which corresponds to a rest mass energy of about 1.8 times joules. But the Sun's gravitational binding energy is approximately minus 3.8 times 1041 joules. This negative energy doesn't cancel out the positive rest mass energy entirely, but it represents a significant energetic debt that keeps the Sun gravitationally bound. When we scale up to galaxy clusters containing thousands of individual galaxies, the gravitational debts become astronomical. The Coma cluster, containing over 1,000 galaxies spread across millions of light years, has a gravitational binding energy of roughly minus 1051 joules. This enormous negative energy exactly balances a corresponding amount of positive mass energy, maintaining the cosmic energy equilibrium we discussed earlier. But gravitational debt operates according to rules that defy everyday intuition. Unlike financial debt, which typically grows through interest and penalties, gravitational debt can actually decrease through certain physical processes. When stars explode as supernovas and scatter their material throughout space, they're partially paying down the gravitational debt accumulated during their formation. The explosion reduces the binding energy of the stellar material, converting negative gravitational potential energy back into positive kinetic energy. The concept of gravitational debt helps explain one of the most puzzling features of cosmic evolution. How did the universe create so much structure and complexity while maintaining perfect energy balance? The answer lies in understanding that structure formation isn't a process of energy creation, but rather a process of debt accumulation. Every galaxy, every star, every planet that forms increases the universe's total gravitational debt while creating corresponding amounts of positive mass energy. Black holes represent the ultimate example of gravitational debt in the cosmos. These objects are so gravitationally bound that their binding energy approaches their rest mass energy. The supermassive black hole at the center of our galaxy, Sagittarius Asterisk, has accumulated gravitational debt equivalent to approximately 4 million solar masses. This enormous negative energy is balanced by the positive mass energy of the black hole itself. But the debt is so large that it fundamentally alters the geometry of spacetime in the surrounding region. The formation of black holes through stellar collapse illustrates how gravitational debt can grow catastrophically under certain conditions. When a massive star exhausts its nuclear fuel and can no longer generate enough pressure to balance gravitational attraction, the star's core collapses in milliseconds. This collapse dramatically increases the gravitational binding energy, creating a debt so large that it warps spacetime to the point where not even light can escape. Einstein's theory of general relativity provides the mathematical framework for understanding how gravitational debt curves spacetime geometry. The Einstein field equations show that mass energy and gravitational binding energy together determine the curvature of spacetime. Regions with large gravitational debts create deeper curvature, which we experience as stronger gravitational fields. This relationship between debt and geometry has led to surprising predictions that have been confirmed by observation. Gravitational lensing occurs when light passes near massive objects with large gravitational debts. The curved spacetime around these objects bends the light's path, creating distorted images of background sources. The amount of lensing is directly related to the total gravitational debt accumulated by the lensing mass. The recent detection of gravitational waves by LIGO and Virgo provides direct evidence for how gravitational debt operates during extreme cosmic events. When two black holes spiral together and merge, they're combining their individual gravitational debts into a single, larger debt. The gravitational waves emitted during this process carry away energy, slightly reducing the total debt of the merged system. This energy loss is what causes the black holes to spiral inward rather than maintaining stable orbits. Dark matter adds another layer of complexity to cosmic gravitational debt. Observations of galaxy rotation curves and gravitational lensing reveal that galaxies contain far more gravitational binding energy than can be accounted for by visible matter alone. This dark matter contributes enormous amounts of negative gravitational energy that must be balanced by corresponding positive energy contributions to maintain cosmic energy balance. The interplay between dark matter and ordinary matter in cosmic structure formation represents a complex dance of debt accumulation and energy redistribution. Computer simulations show that dark matter halos form first through gravitational collapse, accumulating negative binding energy that creates potential wells for ordinary matter to fall into. The subsequent formation of stars and galaxies within these dark matter halos represents a secondary level of debt accumulation. Cosmic inflation provides insights into how gravitational debt might have originated in the early universe. During the inflationary epoch, rapid expansion of space created gravitational potential energy as matter became separated across vast distances. This potential energy represents a form of gravitational debt that drives subsequent structure formation as matter falls back together under its own gravitational attraction. The concept of gravitational debt also helps explain the accelerating expansion of the universe driven by dark energy. As space expands, the average density of matter decreases, which reduces the total gravitational binding energy of the universe. This reduction in gravitational debt must be balanced by increases in other forms of energy, specifically the dark energy that drives acceleration. Quantum field theory in curved spacetime reveals additional subtleties in how gravitational debt operates at the quantum level. Virtual particle creation and annihilation near massive objects is influenced by the local gravitational field, which affects the energy balance between positive and negative virtual particles. This quantum contribution to gravitational energy represents a correction to the classical picture of gravitational debt. The holographic principle suggests that gravitational debt might be fundamentally related to the information content stored on the surfaces of gravitationally bound systems. According to this principle, all the information inside a gravitational system is encoded on its boundary surface. The gravitational binding energy might thus be connected to the entropy and information content of the system, creating links between gravitational debt and information theory. Consciousness and biological systems operate within cosmic gravitational debt through their embodiment in material systems bound by gravity. Your brain processes information using neural networks that exist within Earth's gravitational potential well. The energy transformations that enable thought and consciousness occur within the context of gravitational binding energy that connects your biological system to larger cosmic energy flows. The precise balance between positive mass energy and negative gravitational debt across cosmic scales suggests fundamental principles of physics that ensure perfect energy conservation. This balance appears to be maintained dynamically as structures form and evolve, with feedback mechanisms that prevent runaway energy creation or destruction. Understanding these mechanisms might be key to resolving fundamental questions about cosmic evolution and the nature of dark energy. Gravitational debt thus emerges as a fundamental organizing principle of cosmic evolution, determining how matter can clump together to form structures while maintaining perfect energy balance. This debt isn't a liability that limits cosmic evolution. It is an enabling constraint that allows the universe to create complexity and beauty while respecting the iron laws of energy conservation. Every star that shines, every galaxy that spirals, every planet that orbits represents a sophisticated balance between positive energy creation and negative gravitational debt accumulation. Chapter 3. Quantum Ledger. Deep beneath the Swiss Alps in the particle accelerators of CERN, physicists routinely observe something that shouldn't exist according to classical physics. Particles that appear spontaneously from empty space exist for impossibly brief moments and then disappear back into nothingness. These virtual particles represent the universe as most sophisticated accounting system, a quantum ledger that continuously balances positive and negative energy through transactions that occur trillions of times per second in every cubic centimeter of space. The quantum vacuum, once thought to be the perfect embodiment of nothingness, has revealed itself to be a seething ocean of energy fluctuations that never quite cancel to zero, but maintain perfect average balance over time. These fluctuations don't just influence particle physics experiments, they shape the fundamental structure of reality, determining everything from the magnetic properties of electrons to the expansion rate of the universe itself. To understand how the quantum ledger operates, we need to delve into Heisenberg's uncertainty principle, which states that energy and time cannot both be measured with perfect precision simultaneously. This uncertainty creates what physicists call an energy loan from the quantum vacuum. Virtual particle pairs can borrow energy from empty space to briefly exist, as long as they repay this energy quickly enough that the uncertainty principle prevents the loan from being detected. The mathematics of virtual particle creation reveals the extraordinary scale of quantum bookkeeping. In a region of space the size of a proton, virtual electron-positron pairs appear and disappear approximately 1,021 times per second. Each creation event borrows about 1.6 times 10⁻13 joules of energy from the vacuum, while each annihilation event repays this energy with perfect precision. The quantum ledger processes more transactions per second than all the financial markets on Earth combined. But virtual particles aren't just mathematical abstractions. They have measurable physical effects that confirm the reality of quantum energy borrowing. The Casimir effect, first observed by Dutch physicist Hendrik Casimir in 1948, demonstrates that virtual particles can exert real forces on macroscopic objects. When two conducting plates are placed very close together in a vacuum, they slightly alter the virtual particle population between them, creating a small but measurable attractive force. The Casimir effect occurs because the conducting plates restrict which virtual particle wavelengths can exist in the narrow gap between them. This restriction reduces the energy density of virtual particles between the plates compared to the surrounding vacuum, creating a pressure difference that pushes the plates together. The effect has been measured with extraordinary precision, confirming predictions of quantum field theory to within fractions of a percent. Recent experiments have revealed even more exotic effects of quantum energy borrowing. Dynamic Casimir effect experiments use rapidly moving boundaries to convert virtual particles into real particles, essentially forcing the quantum vacuum to make its energy loans permanent. These experiments demonstrate that the distinction between virtual and real particles is more fluid than previously understood. Virtual particles can become real if sufficient energy is provided to pay off their quantum debt. The quantum ledger extends far beyond virtual particle creation into the realm of quantum field fluctuations that permeate all of spacetime. Every quantum field, electromagnetic, electron, quark, neutrino, Higgs, and others, contributes its own pattern of energy borrowing and repayment. The total energy density of quantum vacuum fluctuations, when calculated naively, yields an impossibly large number that would curve space-time so severely that the universe couldn't exist. This apparent contradiction between theoretical predictions and observational reality is known as the cosmological constant problem, one of the most profound puzzles in modern physics. The calculated vacuum energy density exceeds the observed dark energy density by a factor of 10,120, a discrepancy so enormous that it suggests fundamental gaps in our understanding of how the quantum ledger operates at cosmic scales. Several proposed solutions to the cosmological constant problem involve sophisticated cancellation mechanisms in the quantum ledger. Supersymmetry theories propose that every known particle has a superpartner with opposite statistical properties, such that bosonic and fermionic virtual particles make exactly equal and opposite contributions to vacuum energy. String theory suggests that extra spatial dimensions provide additional channels for vacuum energy cancellation. The anthropic principle offers another perspective. Perhaps the quantum ledger is fine-tuned to produce precisely the right amount of dark energy to allow structure formation and biological evolution. In this view, the apparent impossibility of calculating vacuum energy density correctly reflects the fact that we exist in one of the rare universes where quantum energy borrowing is balanced just right to permit the existence of observers. Quantum electrodynamics, QED, provides the most precisely tested framework for understanding quantum energy bookkeeping in electromagnetic interactions. Virtual photon exchange between charged particles creates forces, magnetic moments, and other measurable effects that have been verified to extraordinary precision. The anomalous magnetic moment of the electron, calculated using QED virtual particle corrections, agrees with experimental measurements to 12 decimal places. But QED also reveals subtle violations of classical energy conservation that are permitted by quantum mechanics. Virtual particles can carry more energy than classical conservation laws would allow, as long as they exist for short enough times that the energy violation remains within the uncertainty principle bounds. This quantum energy borrowing enables processes that would be impossible in classical physics. The concept of negative energy states plays a crucial role in quantum field theory's energy accounting. Antiparticles can be understood as negative energy solutions to the Dirac equation, traveling backward in time. When particle-antiparticle pairs are created from the vacuum, the total energy remains zero because the positive energy of the particle is balanced by the negative energy of the antiparticle. This interpretation helps explain how the quantum ledger maintains perfect energy balance even during dramatic particle creation events. In high-energy collisions at particle accelerators, hundreds of new particles can be created from the kinetic energy of the colliding beams. But quantum field theory shows that this apparent energy creation is actually energy redistribution. The positive energy of newly created particles is balanced by negative energy contributions from virtual particle interactions. Hawking radiation from black holes represents one of the most exotic examples of quantum energy accounting. According to Hawking's calculation, virtual particle pairs created near the event horizon can be split apart by the black hole's intense gravitational field. One member of the pair falls into the black hole while the other escapes as real radiation. The escaping particle has positive energy, while the particle falling into the black hole carries negative energy that reduces the black hole's mass. This process appears to violate energy conservation. Positive energy radiation escapes while the black hole loses mass. But the quantum ledger maintains perfect balance through the negative energy of the infalling particle. The black hole effectively pays for the escaping radiation by consuming negative energy, causing it to slowly evaporate over time. For stellar mass black holes, this evaporation process would take longer than the current age of the universe. The information paradox in black hole physics reveals additional complexities in quantum energy accounting. If black holes evaporate completely through Hawking radiation, what happens to the information that fell into them? The quantum ledger must somehow maintain both energy conservation and information conservation. But the mechanisms for achieving this dual conservation remain mysterious. Quantum entanglement creates non-local correlations that appear to challenge classical understanding of energy conservation. When entangled particles are separated by vast distances, measurements on one particle instantaneously influence the other, seemingly violating the speed of light limit. But careful analysis shows that no energy is transmitted through the entanglement connection. The quantum ledger respects relativistic constraints even in non-local quantum phenomena. The role of observers in quantum energy accounting adds another layer of complexity. Quantum measurements appear to collapse wave functions and determine which virtual particles become real, potentially influencing the energy balance of quantum systems. Some interpretations suggest that consciousness itself plays a role in quantum energy bookkeeping by determining when and how energy loans are repaid. Cosmic inflation provides a cosmological context for understanding quantum energy borrowing on the largest scales. During inflation, quantum vacuum fluctuations were stretched to cosmic sizes, creating the density perturbations that later grew into galaxies and galaxy clusters. This process appears to create enormous amounts of positive energy from quantum fluctuations. But inflationary models show that this energy creation is balanced by corresponding increases in negative gravitational potential energy. The quantum ledger thus operates across every scale from the subatomic to the cosmological, maintaining perfect energy balance through mechanisms that blend classical conservation laws with quantum uncertainty. Virtual particles, vacuum fluctuations, and quantum field interactions represent the universe as most fundamental accounting system, a system so sophisticated that it enables the creation of matter, energy, and structure, while never violating the cosmic constraint that total energy must sum to zero. Understanding the quantum ledger provides crucial insights into why the universe can appear to create energy from nothing while actually maintaining perfect conservation. Every particle creation, every field interaction, every quantum measurement represents a transaction in this cosmic accounting system where energy can be borrowed freely as long as it is repaid within the constraints of quantum uncertainty. This borrowing and repayment cycle enables the rich phenomena of quantum physics while ensuring that the universal energy budget always balances perfectly. Chapter 4. Cosmic Bookkeeping. At the Planck Collaboration Headquarters in Paris, cosmologist Jean-Claude Puget reviews data from humanity's most precise map of the early universe. Temperature measurements of the cosmic microwave background radiation, accurate to within millionths of a degree. What this data reveals is extraordinary. The universe's energy budget has remained perfectly balanced for 13.8 billion years, maintaining a cosmic equilibrium so precise that it suggests reality operates according to accounting principles more stringent than any earthly financial system. The cosmic microwave background carries fossilized evidence of the universe's energy balance from just 380,000 years after the Big Bang, when the cosmos first became transparent to light. The tiny temperature fluctuations embedded in this radiation represent quantum energy fluctuations that would stretch the cosmic scales during inflation. These fluctuations had to satisfy perfect energy conservation constraints while providing the seeds for all future cosmic structure. To understand the sophistication of cosmic bookkeeping, consider the energy budget of the observable universe. The total mass energy content includes approximately 5% ordinary matter, 25% dark matter, and 70% dark energy. Each of these components contributes to cosmic energy balance in different ways, and the ratios between them appear to be fine-tuned to maintain perfect equilibrium while allowing complex structures to form. Ordinary matter provides the positive energy that we directly observe, the mass energy of protons, neutrons, electrons, and photons that make up stars, planets, and living organisms. This visible component of cosmic energy corresponds to roughly 4,1053 joules distributed across the observable universe. But this enormous quantity of positive energy must be exactly balanced by corresponding negative energy contributions to maintain zero total energy. Dark matter contributes approximately 5 times more mass energy than ordinary matter, but its gravitational effects reveal that it participates in cosmic energy balance through its binding energy with ordinary matter and itself. Dark matter halos surrounding galaxies create gravitational potential wells that contain negative binding energy proportional to the square of the halo mass. This negative energy exactly balances the positive rest mass energy of the dark matter particles. Dark energy represents the most mysterious component of cosmic bookkeeping. This energy density appears to remain constant as the universe expands, which naively suggests that dark energy is being continuously created as new space comes into existence. But cosmic energy balance requires that this apparent energy creation be balanced by corresponding negative energy contributions that maintain zero total energy. The accelerating expansion driven by dark energy creates a cosmic accounting puzzle that physicists are still working to solve. As space expands, the energy density of matter and radiation decreases due to dilution, while dark energy density remains constant. This evolution changes the relative contributions of different energy components to the cosmic budget while somehow maintaining perfect overall balance. Recent measurements from the Dark Energy Survey and other cosmological observations have revealed that dark energy exhibits an equation of state parameter very close to -1, corresponding to a cosmological constant. This value has profound implications for cosmic energy balance because it is precisely the value required to maintain constant energy density during cosmic expansion. The precision of this measurement suggests that cosmic bookkeeping operates with extraordinary accuracy. The concept of cosmic inflation provides crucial insights into how energy balance is maintained during dramatic cosmic evolution. During the inflationary epoch, the universe expanded by at least 60 orders of magnitude in a tiny fraction of a second. This expansion appears to create enormous amounts of space, matter, and energy, but inflationary models show that energy conservation is maintained through the interplay between inflated field energy and gravitational potential energy. The inflated field that drove cosmic inflation acts like a cosmic energy reservoir that can borrow energy from the vacuum to power exponential expansion. As the field slowly rolls down its potential energy curve, it converts potential energy into the kinetic energy of cosmic expansion. But this energy conversion process maintains perfect balance because the expansion simultaneously creates negative gravitational potential energy proportional to the square of the scale factor. The end of inflation, called reheating, represents perhaps the most dramatic energy transfer event in cosmic history. The coherent oscillations of the inflated field decay into elementary particles, converting the field's energy into the hot, dense plasma that would eventually form the cosmic microwave background. This energy conversion process had to maintain perfect energy conservation while creating all the matter and radiation in the observable universe. Big Bang nucleosynthesis provides another window into cosmic energy accounting. During the first few minutes after the Big Bang, nuclear reactions converted some of the universe's protons and neutrons into light elements like helium and lithium. These nuclear reactions involve precise energy balances between nuclear binding energy, thermal energy, and expansion energy that determined the final abundance ratios of light elements. The observed abundances of light elements provide crucial tests of cosmic energy balance during nucleosynthesis. The ratio of helium to hydrogen, the abundance of deuterium, and the trace amounts of lithium all depend sensitively on the energy density and expansion rate of the early universe. The precise agreement between theoretical predictions and observational measurements confirms that energy conservation was maintained throughout this crucial epoch. Cosmic structure formation represents an ongoing energy redistribution process that maintains perfect balance while creating the galaxies, stars, and planets we observe today. As dark matter halos collapse under their own gravity, they convert kinetic energy into negative gravitational binding energy. The subsequent formation of stars within these halos involves additional energy conversions between gravitational potential energy, thermal energy, and nuclear binding energy. The cosmic web of large-scale structure provides compelling evidence for how energy balance shapes cosmic evolution. Computer simulations of structure formation show that the pattern of galaxies, filaments, and voids emerges naturally from gravitational evolution of initial density fluctuations. These simulations must carefully track energy conservation throughout billions of years of cosmic evolution to reproduce observed large-scale structure. Black holes play a special role in cosmic energy, accounting through their enormous gravitational binding energies and their interactions with surrounding matter. When matter falls into a black hole, it releases gravitational potential energy that can power some of the most energetic phenomena in the universe, including quasars and gamma-ray bursts. These energy releases represent conversions of gravitational potential energy into electromagnetic radiation and kinetic energy of outflowing material. The recent discoveries of gravitational waves have provided new tools for studying cosmic energy balance. The merger of two black holes or neutron stars releases enormous amounts of energy in the form of gravitational waves, as much as the combined power output of all stars in the observable universe, but concentrated into a few seconds. This energy release represents the conversion of orbital kinetic energy and gravitational binding energy into gravitational radiation. Dark energy's role in cosmic acceleration creates subtle effects in energy accounting that are just beginning to be understood. As space expands faster due to dark energy, more distant objects recede from us at higher velocities. This recession changes the apparent energy of photons through cosmological redshift, creating complex feedback effects between dark energy and electromagnetic radiation. The anthropic principle suggests that cosmic energy balance might be fine-tuned to enable the existence of observers. Among all possible values of dark energy density, matter density, and other cosmological parameters, only a narrow range allows for the formation of stars, planets, and biological evolution. This fine-tuning could reflect selection effects in a multiverse, or it could indicate fundamental principles of physics that naturally maintain optimal energy balance. Quantum mechanics adds another layer of complexity to cosmic bookkeeping through zero-point energy fluctuations and virtual particle creation throughout space. The total zero-point energy of all quantum fields in the universe should contribute to cosmic energy density, but calculating this contribution yields absurdly large values that would prevent cosmic structure formation. This cosmological constant problem suggests that cosmic energy balance involves sophisticated cancellation mechanisms between different quantum contributions. The holographic principle proposes that all the information in a three-dimensional cosmic region is encoded on its two-dimensional boundary surface. This principle has implications for cosmic energy accounting because it suggests that energy density in cosmic volumes might be fundamentally related to information density on cosmic surfaces. The energy required to encode information could contribute to dark energy density and cosmic acceleration. Cosmic bookkeeping thus emerges as a fundamental organizational principle that constrains cosmic evolution while enabling the emergence of complex structures and phenomena. The perfect energy balance maintained across 13.8 billion years of cosmic history suggests either extraordinary fine-tuning or deep principles of physics that naturally ensure energy conservation. Understanding these principles might be the key to resolving fundamental puzzles about dark energy, cosmic acceleration, and the ultimate fate of the universe. Every astronomical observation, from the cosmic microwave background to gravitational wave detections to dark energy measurements, provides data points for the cosmic ledger that tracks energy balance across space and time. This ledger reveals a universe that operates with accounting precision that exceeds human financial systems by many orders of magnitude, maintaining perfect energy conservation while enabling the rich tapestry of cosmic phenomena we observe. Chapter 5. Dark Mysteries at the Vera Rubin Observatory in Chile. Astronomer Vera Rubin peers through the eyepiece of her telescope, tracking the rotation of stars around the outer edges of the Andromeda Galaxy. According to Newton's laws, these distant stars should be moving slowly, barely held in orbit by the faint gravitational pull of the galaxy's central regions. Instead, they're racing around at velocities that should fling them into intergalactic space. Her measurements reveal that galaxies contain far more gravitational influence than can be accounted for by visible matter, a discovery that would lead to one of the most profound mysteries in cosmic energy accounting. What Rubin had discovered was evidence for dark matter, an invisible form of matter that outweighs all the stars, planets, and gas clouds in the universe by a factor of 5 to 1. This dark matter doesn't emit, absorb, or reflect electromagnetic radiation, making it essentially invisible to telescopes. Yet its gravitational effects dominate the energy budget of every cosmic structure, from individual galaxies to the largest superclusters. The existence of dark matter fundamentally alters our understanding of cosmic energy balance. The matter we can see, protons, neutrons, electrons, and photons, represents only about 16% of the universe's total matter content. The remaining 84% consists of dark matter particles whose nature remains completely unknown despite decades of intensive searches. This invisible majority plays a crucial role in cosmic bookkeeping by providing the gravitational scaffolding upon which visible structures form. Dark matter's contribution to cosmic energy accounting becomes clear when we examine galaxy formation simulations. Computer models show that ordinary matter alone cannot explain how galaxies formed so quickly in the early universe. The gravitational attraction of ordinary matter is too weak to pull gas clouds together fast enough to form the first galaxies within the first billion years after the Big Bang. Dark matter halos must have formed first, creating deep gravitational potential wells that ordinary matter could fall into. These dark matter halos represent enormous reservoirs of negative gravitational binding energy. A typical galaxy like the Milky Way sits within a dark matter halo containing about 1,012 solar masses spread across hundreds of thousands of light years. The gravitational binding energy of this halo is approximately 1051 joules, negative energy that must be balanced by corresponding positive energy contributions to maintain cosmic equilibrium. But dark matter is only part of the cosmic energy mystery. In 1998, observations of distant supernovas revealed an even more startling discovery. The expansion of the universe is accelerating. This acceleration implies the existence of dark energy, a form of energy density that permeates all of space and exerts negative pressure, causing space itself to expand faster and faster over time. Dark energy represents approximately 70% of the total energy density in the universe, making it the dominant component of cosmic energy accounting. Unlike matter and radiation, which dilute as the universe expands, dark energy density remains approximately constant. This means that as the universe grows larger, the total amount of dark energy increases proportionally to the volume of space. The constancy of dark energy density creates a profound puzzle for energy conservation. If dark energy density doesn't dilute with expansion, then new dark energy appears to be created continuously as new space comes into existence. This apparent violation of energy conservation requires sophisticated explanation to maintain cosmic energy balance. One possible resolution involves negative pressure effects in general relativity. Dark energy with an equation of state parameter W equals -1 exerts negative pressure equal in magnitude to its energy density. This negative pressure does negative work as the universe expands, exactly compensating for the energy increase due to constant energy density. The cosmic energy ledger remains balanced because positive energy creation is exactly offset by negative work done by dark energy pressure. The lambda-CDM model, our current standard model of cosmology, incorporates both dark matter, CDM stands for cold dark matter, and dark energy, represented by the cosmological constant lambda, into a comprehensive framework for cosmic evolution. This model successfully explains a wide range of astronomical observations, from the cosmic microwave background to large-scale structure to supernova distances. But the lambda-CDM model raises deep questions about the nature of cosmic energy balance. The cosmological constant lambda represents the energy density of empty space itself, the zero-point energy of quantum fields that permeates the vacuum. Calculating this quantum vacuum energy density from first principles yields values that are 10120 times larger than the observed dark energy density, creating what physicists call the worst prediction in the history of science. This cosmological constant problem suggests that cosmic energy accounting involves incredibly precise cancellations between different contributions to vacuum energy density. Quantum field theory predicts enormous positive contributions from virtual particle fluctuations, but these must somehow be almost perfectly cancelled by unknown negative contributions to yield the tiny observed dark energy density. Several exotic forms of dark energy have been proposed to explain cosmic acceleration without invoking a cosmological constant. Quintessence models involve slowly evolving scalar fields that can change their energy density over time. Phantom dark energy has W-1, causing its energy density to increase with cosmic expansion. These alternative models change the cosmic energy balance in different ways, while potentially avoiding some problems with the cosmological constant. The discovery of the Higgs boson in 2012 provided new insights into how scalar fields might contribute to cosmic energy balance. The Higgs field has a non-zero vacuum expectation value throughout space, giving mass to elementary particles through spontaneous symmetry breaking. This field represents a form of vacuum energy that contributes to cosmic energy density, though its contribution is many orders of magnitude smaller than the total dark energy density. Dark matter detection experiments have searched for direct evidence of dark matter particles interacting with ordinary matter. Underground laboratories, like the Large Underground Xenon Lux experiment and the Cryogenic Dark Matter Search (CDMS), use sensitive detectors to look for the tiny energy deposits that would be created if dark matter particles collided with detector nuclei. Despite increasingly sensitive searches, no definitive dark matter signals have been detected. The absence of direct detection signals has led to alternative theories about the nature of dark matter. Axions, hypothetical particles originally proposed to solve problems in quantum chromodynamics, could constitute dark matter if they exist in sufficient abundance. Sterile neutrinos, additional neutrino species that interact only through gravity, represent another dark matter candidate that would minimally disrupt the standard model of particle physics. Some physicists have proposed that dark matter and dark energy might not exist as separate phenomena, but rather emerge from modifications to gravity itself. Modified Newtonian dynamics, MOND, attempts to explain galaxy rotation curves by changing how gravity behaves at very low accelerations. Extra-dimensional theories suggest that gravity might leak into higher dimensions, altering its strength on cosmic scales. The interplay between dark matter and dark energy creates complex feedback effects in cosmic evolution. Dark matter provides the gravitational framework for structure formation, while dark energy's acceleration works against gravitational collapse. The precise balance between these competing effects determines which structures can form and when, influencing everything from galaxy formation to star formation rates. Recent observations of cosmic structure have provided new constraints on dark sector physics. The cosmic web of galaxy filaments and voids preserves information about how dark matter and dark energy have influenced structure formation over billions of years. Baryon acoustic oscillations, sound waves that traveled through the early universe, provide standard rulers for measuring cosmic expansion and constraining dark energy properties. The discovery of gravitational waves has opened new windows into dark sector physics. Binary black hole mergers provide information about the mass function of compact objects, which could be influenced by dark matter interactions. The merger rates of black holes and neutron stars might be affected by dark matter halos around these objects, providing indirect probes of dark matter properties. Cosmic microwave background polarization measurements have revealed subtle signatures of dark matter and dark energy in the early universe. The polarization patterns preserve information about density fluctuations and gravitational effects during recombination when the universe first became transparent. These measurements provide independent tests of dark sector models and help constrain the energy balance between different cosmic components. The anthropic principle suggests that dark matter and dark energy densities might be fine-tuned to enable the formation of structures capable of supporting life. If dark matter were too abundant, structures would form too early and be too dense for star formation. If dark energy were too dominant, acceleration would prevent any structure formation. The observed values appear to be optimized for maximum structure formation and biological evolution. Quantum field theory in expanding spacetime provides frameworks for understanding how dark energy might arise from fundamental physics. Vacuum energy fluctuations in curved spacetime can contribute to the stress energy tensor that drives cosmic expansion. Loop quantum cosmology suggests that quantum geometry effects might naturally generate dark energy-like behavior without requiring a cosmological constant. The future evolution of the universe depends critically on the properties of dark matter and dark energy. If dark energy remains constant, the universe will enter an era of exponential expansion that eventually separates all cosmic structures. If dark energy decays or changes sign, the cosmic expansion might reverse, leading to a big crunch. Understanding dark sector physics is essential for predicting the ultimate fate of cosmic energy balance. Dark mysteries thus represent the frontier of cosmic energy accounting, involving unknown forms of matter and energy that dominate the cosmic budget while remaining almost completely mysterious. These dark components are not peripheral curiosities, but fundamental aspects of cosmic energy balance that determine how structures form, how the universe evolves, and whether energy conservation is maintained throughout cosmic history. Solving the mysteries of dark matter and dark energy might be the key to understanding the deepest principles that govern cosmic energy accounting. Chapter 6. Field Equations. In the autumn of 1915, Albert Einstein sat in his study in Berlin, wrestling with equations that would revolutionize humanity's understanding of energy, space, and time. After months of intense mathematical struggle, he finally arrived at 10 elegant equations that would become known as the Einstein field. Equations, mathematical expressions that reveal how energy and matter curve the fabric of space-time itself. Hidden within these equations was a profound truth about cosmic energy balance. Gravity is not a force, but geometry, and this geometry automatically ensures that energy conservation is maintained throughout the universe. The Einstein field equations can be written compactly as G equals 8T, where G represents the curvature of spacetime and T represents the energy and matter content. This deceptively simple relationship encodes one of the most profound insights in physics. Matter tells spacetime how to curve, and curved spacetime tells matter how to move. But embedded within this geometric relationship are powerful constraints that ensure perfect energy conservation even in the most extreme cosmic environments. To understand how the field equations maintain energy balance, consider what happens when energy is distributed throughout space. Every concentration of mass energy creates a curvature in spacetime that corresponds to what we experience as gravitational attraction. This curvature represents negative gravitational potential, energy that exactly balances the positive mass energy that created it. The geometry of spacetime automatically performs the cosmic bookkeeping we discussed earlier. The mathematical elegance of this energy balance emerges from the Bianchi identities, geometric relationships that are automatically satisfied by any solution to Einstein's equations. These identities ensure that the divergence of the stress-energy tensor vanishes, which is the mathematical statement of local energy momentum conservation. The field equations don't just allow energy conservation. They require it as a fundamental geometric property of spacetime. But Einstein's original equations contained a subtle asymmetry that troubled their creator. When he applied them to cosmology, seeking solutions that described the universe as a whole, he found that static cosmological solutions were unstable. The universe described by his equations would either expand or contract. It could not remain perfectly balanced in a static state. This prediction seemed to contradict the prevalent view of the time that the cosmos was eternal and unchanging. To restore cosmic stability, Einstein introduced the cosmological constant lambda, an additional term in his field equations that could provide a repulsive force to balance gravitational attraction. The modified field equations became G plus G equals 8T, where the new term represents the energy density of empty space itself. This cosmological constant would later prove to be one of the most prescient additions in the history of physics. The cosmological constant represents a form of energy density that remains constant throughout space and time. Unlike ordinary matter and radiation, which dilute as the universe expands, cosmological constant energy density stays fixed even as space grows. This constancy seems to violate energy conservation. New energy appears to be created as new space comes into existence. But the field equations reveal that energy conservation is maintained through the negative pressure associated with the cosmological constant. The pressure associated with dark energy is negative, meaning that dark energy exerts tension rather than compression. As the universe expands against this tension, the negative pressure does negative work that exactly compensates for the apparent energy creation. The total energy content of any expanding region remains constant because the increase in dark energy is balanced by the negative work done by dark energy pressure. This mechanism resolves one of the most puzzling aspects of cosmic energy balance: how the universe can accelerate its expansion while conserving energy. Observations of distant supernovas in 1998 confirmed that cosmic expansion is indeed accelerating, driven by dark energy that comprises roughly 70% of the cosmic energy budget. The field equations show that this acceleration is perfectly consistent with energy conservation when the pressure effects of dark energy are properly included. The field equations also reveal how gravitational waves maintain energy balance during their propagation through spacetime. When massive objects accelerate, they create ripples in the curvature of spacetime that carry energy away from the source. The recent detections of gravitational waves by LIGO and Virgo have confirmed that these waves carry exactly the amount of energy predicted by the field equations, providing direct verification of energy conservation in strong field gravity. Black holes represent the most extreme test of energy conservation in Einstein's theory. When matter falls into a black hole, it appears to disappear from the observable universe, potentially violating energy conservation. But the field equations show that the energy is not destroyed. It becomes part of the black hole's mass energy, increasing the curvature of spacetime around the event horizon. The total energy of the spacetime region, including the black hole, remains constant. Hawking's discovery that black holes emit thermal radiation created an apparent paradox for energy conservation. The radiation carries positive energy away from the black hole, while the black hole loses mass, seemingly creating energy from nothing. But detailed analysis using the field equations reveals that the energy balance is maintained through negative energy flux into the black hole. Virtual particles with negative energy fall into the black hole, reducing its mass and providing the energy that escapes as Hawking radiation. The field equations have also illuminated the energy balance during cosmic inflation, the period of exponential expansion in the early universe. The inflated field that drives inflation has negative pressure, similar to dark energy, but much stronger. As the inflated field slowly evolves, it converts its potential energy into the expansion energy of spacetime while maintaining perfect energy conservation through pressure work effects. Quantum field theory in curved spacetime extends the field equations to include quantum effects, revealing new subtleties in energy balance. Virtual particle creation is enhanced near massive objects due to the tidal effects of spacetime curvature. This quantum contribution to the stress-energy tensor must be included in the field equations, creating feedback effects between quantum vacuum fluctuations and spacetime geometry. The renormalization procedures required to make sense of quantum field theory in curved spacetime reveal deep connections between energy conservation and the structure of physical theories. Infinite vacuum energy contributions must be carefully regulated and renormalized to extract finite, physically meaningful results. These procedures suggest that energy balance in quantum gravity might require principles beyond those encoded in the classical field equations. The holographic principle, which proposes that all information in a gravitational system is encoded on its boundary, has implications for energy conservation in the field equations. If the physics inside a region of spacetime is completely determined by information on its boundary, then energy balance might be fundamentally related to information conservation on these boundaries. This connection could provide new insights into how the field equations maintain energy conservation in quantum gravitational systems. String theory attempts to extend the field equations to include quantum gravity effects and extra spatial dimensions. In string theory, the field equations become part of a larger set of consistency conditions that include energy conservation, charge conservation, and other symmetry requirements. The additional dimensions provide new channels for energy balance that might help resolve puzzles like the cosmological constant problem. The study of cosmological phase transitions has revealed how the field equations govern energy balance during dramatic changes in the structure of spacetime. During inflation, the universe underwent a phase transition from a high-energy vacuum state to a lower-energy state, releasing enormous amounts of energy that became the matter and radiation we observe today. The field equations ensure that this energy release maintains perfect conservation through the interplay between field energy and gravitational potential energy. Cosmic strings, topological defects that might have formed during early universe phase transitions, provide another example of how the field equations maintain energy balance. These one-dimensional objects have enormous energy densities but create spacetime geometries that ensure the total energy of any region containing a cosmic string segment remains finite. The gravitational effects of cosmic strings are completely determined by their energy per unit length. The field equations have practical applications for understanding energy balance in astrophysical systems. Neutron stars, white dwarfs, and other compact objects exist in hydrostatic equilibrium where gravitational attraction is balanced by pressure gradients. The Tolman-Oppenheimer-Volkoff equations, derived from the field equations, determine the maximum masses these objects can have while maintaining stable energy balance. Active galactic nuclei powered by supermassive black holes demonstrate energy balance on cosmic scales. Matter falling into these black holes releases gravitational potential energy that can power some of the most luminous objects in the universe. The field equations show that the energy output of these systems is ultimately derived from the mass energy of infalling matter, converted to radiation through gravitational interactions. The detection of cosmic microwave background polarization has provided new tests of energy conservation in the field equations. Gravitational waves in the early universe should have left distinctive signatures in the polarization patterns of the cosmic microwave background. The absence of these signatures at expected levels places constraints on inflationary models and tests the energy balance predictions of the field equations. Future tests of the field equations will probe energy conservation in increasingly extreme regimes. The Event Horizon Telescope has begun imaging the spacetime geometry around supermassive black holes, providing direct tests of the field equations in strong gravitational fields. Gravitational wave interferometers will detect mergers of black holes and neutron stars, testing energy conservation during the most violent events in the universe. The field equations thus provide the mathematical framework for understanding how energy balance is maintained throughout the cosmos. From the smallest quantum fluctuations to the largest cosmic structures, Einstein's geometric vision ensures that energy is neither created nor destroyed, but rather redistributed between matter, radiation, and the curvature of spacetime itself. This geometric approach to energy conservation represents one of the most beautiful and successful theories in physics, demonstrating that the deepest laws of nature can be expressed as elegant mathematical relationships between energy and the structure of reality. Chapter 7. Vacuum Secrets. In the laboratories of the National Institute of Standards and Technology, physicist Steve Lamoureux carefully aligns two perfectly flat metal surfaces separated by a gap smaller than a human hair. According to classical physics, these surfaces in a vacuum should experience no forces between them. But when Lamoureux makes his measurements, he finds that the surfaces are pulled together by a mysterious force that emerges from apparently empty space. This is the Casimir effect, direct evidence that the quantum vacuum is not empty, but filled with energy fluctuations that can exert real physical forces. The quantum vacuum represents one of the most profound challenges to our understanding of energy balance in physics. Far from being simple nothingness, empty space seethes with virtual particle pairs that appear and disappear in accordance with Heisenberg's uncertainty principle. These quantum fluctuations carry energy, so much energy that naive calculations suggest the vacuum should have an energy density 10,120 times larger than the observed energy density of the universe. This enormous discrepancy between theoretical predictions and observational reality is known as the cosmological constant problem, and it reveals that vacuum energy plays a crucial role in cosmic energy accounting that we don't yet fully understand. The vacuum somehow manages to maintain near-perfect energy balance while exhibiting quantum fluctuations that should, according to straightforward calculations, tear space-time apart? To understand how vacuum energy might contribute to cosmic balance, we need to examine the fundamental nature of quantum fields. Every type of particle, electrons, photons, quarks, neutrinos, corresponds to quantum field that permeates all of spacetime. Even when no real particles are present, these fields exhibit zero-point motion analogous to the vibrations of a guitar string. The total zero-point energy of all quantum fields represents the irreducible energy content of empty space. The mathematics of quantum field theory shows that each mode of each quantum field contributes 1/2 omega to the vacuum energy, whereas Planck's constant and omega is the frequency of the mode. When summed over all possible frequencies up to some cutoff scale, this gives an energy density that scales as the 4th power of the cutoff frequency. Using the Planck scale as a natural cutoff yields vacuum energy densities that exceed the critical density of the universe by more than 100 orders of magnitude. But the Casimir effect demonstrates that vacuum energy has real, measurable consequences. When Lamoure's metal plates are brought close together, they modify the spectrum of virtual photons that can exist between them. Photon wavelengths longer than the plate separation cannot fit between the plates, reducing the energy density of electromagnetic vacuum fluctuations in the gap. This creates a pressure difference that pushes the plates together with a force that decreases as the inverse 4th power of the separation distance. Recent experiments have extended Casimir effect measurements to unprecedented precision, confirming quantum field theory predictions to within fractions of a percent. Experiments with different geometries, spheres, cylinders, rough surfaces, all show that vacuum energy fluctuations create measurable forces exactly as predicted by quantum electrodynamics. These measurements provide compelling evidence that vacuum energy is not merely a theoretical construct, but a physical reality. The dynamic Casimir effect represents an even more dramatic demonstration of vacuum energy manipulation. When boundaries move rapidly enough, they can convert virtual photons into real photons, effectively extracting energy from the quantum vacuum. Experiments using superconducting circuits that simulate moving boundaries have successfully demonstrated this effect, showing that vacuum energy can be converted into observable radiation under appropriate conditions. But the cosmological constant problem suggests that vacuum energy contributions to cosmic expansion are either exactly zero or incredibly precisely tuned. If vacuum energy contributed to dark energy at the level predicted by quantum field theory, the universe would have expanded so rapidly that no structures could form. The fact that we observe a universe with galaxies, stars, and planets indicates that vacuum energy somehow cancels out to extraordinary precision. Supersymmetry provides one possible resolution to the vacuum energy puzzle. In supersymmetric theories, every known particle has a superpartner with opposite statistical properties. Bosonic particles contribute positive vacuum energy, while fermionic particles contribute negative vacuum energy. If supersymmetry were exact, these contributions would cancel perfectly, yielding zero vacuum energy density. The breaking of supersymmetry at accessible energy scales could then generate the small observed dark energy density. String theory offers another perspective on vacuum energy balance through the concept of moduli stabilization. In string theory, the extra spatial dimensions must be compactified to recover four-dimensional physics. The shape and size of these extra dimensions determine the vacuum energy density, and string theory provides mechanisms for stabilizing these moduli at values that yield small vacuum energy. However, achieving the required precision in moduli stabilization remains a significant theoretical challenge. The anthropic principle suggests that vacuum energy might be fine-tuned through selection effects in a multiverse. If different regions of spacetime or different universes have different vacuum energy densities, then only regions with appropriately small vacuum energy can support structure formation and biological evolution. Observers find themselves in universes with small vacuum energy not because of fundamental principles, but because only such universes can support observers. Loop quantum gravity provides insights into vacuum energy from the perspective of discrete spacetime geometry. In this approach, spacetime consists of quantum geometric degrees of freedom that may naturally regulate vacuum energy divergences. The discreteness of space at the Planck scale could provide a natural cutoff that eliminates infinite vacuum energy contributions while preserving the finite effects observed in Casimir experiments. The holographic principle has implications for vacuum energy accounting through its relationship with black hole entropy. If the maximum entropy that can be stored in a region of space is proportional to the area of its boundary rather than its volume, then vacuum energy density might be fundamentally limited by holographic bounds. These bounds could provide natural mechanisms for regulating vacuum energy while maintaining consistency with other physical principles. Quantum error correction has emerged as a new framework for understanding vacuum energy stability. If the vacuum state represents a quantum error-correcting code, then small perturbations would be automatically corrected, maintaining vacuum stability despite quantum fluctuations. This perspective suggests that vacuum energy balance might be maintained through active quantum information processing at the Planck scale. The Unruh effect demonstrates that vacuum energy depends on the observer's state of motion. Accelerating observers detect thermal radiation from the quantum vacuum, while inertial observers see only zero-point fluctuations. This observer dependence suggests that vacuum energy is not a universal property, but rather depends on the reference frame used to define energy. This relativity of vacuum energy could help explain why vacuum contributions to cosmic expansion are so small. Hawking radiation from black holes provides another window into vacuum energy physics. The thermal radiation emitted by black holes arises from vacuum fluctuations near the event horizon, demonstrating that vacuum energy can be converted into real particles under extreme gravitational conditions. The temperature and spectrum of Hawking radiation are completely determined by the black hole's geometry, showing that vacuum energy effects are intimately connected to spacetime curvature. The firewall paradox in black hole physics reveals tensions between different approaches to vacuum energy near event horizons. If vacuum fluctuations become energetic enough to create a firewall that incinerates in falling observers, then vacuum energy could have dramatic effects in strong gravitational fields. Resolving this paradox might require new understanding of how vacuum energy behaves in curved spacetime. Dark energy's relationship to vacuum energy remains one of the deepest puzzles in cosmology. If dark energy corresponds to the cosmological constant, then it represents the energy density of empty space itself. But the observed dark energy density is far smaller than theoretical predictions for vacuum energy, suggesting either remarkable fine-tuning or new physics that naturally suppresses vacuum energy contributions. Quintessence models propose that dark energy might arise from slowly evolving scalar fields rather than vacuum energy. These fields could start with large energy densities in the early universe and slowly decay to the small values observed today. Such models avoid some problems with vacuum energy while introducing new questions about why. Scalar field evolution would proceed in precisely the right way to match observations. Modified gravity theories attempt to explain cosmic acceleration without invoking dark energy or vacuum energy. These models modify Einstein's field equations at large scales, potentially eliminating the need for vacuum energy contributions to cosmic expansion. However, most modified gravity models face challenges in matching the precision of observations achieved by dark energy models. Experimental searches for vacuum energy effects continue to push the boundaries of precision measurement. Atomic interferometry experiments probe vacuum energy fluctuations by measuring tiny forces on atoms. Resonant cavity experiments search for vacuum energy contributions to electromagnetic field oscillations. These experiments might eventually detect vacuum energy effects beyond the Casimir force, providing new insights into vacuum energy physics. The future of vacuum energy research will likely involve increasingly sophisticated quantum technologies. Quantum computers might be able to simulate vacuum energy effects that are too complex for classical calculation. Quantum sensors could detect vacuum energy fluctuations with unprecedented sensitivity. These technologies might finally provide the tools needed to understand how vacuum energy contributes to cosmic energy balance. Vacuum secrets thus represent some of the deepest mysteries in physics, involving energy fluctuations that permeate every point in spacetime, while somehow maintaining extraordinary cancellations that allow the universe to exist. Understanding these secrets might be the key to resolving fundamental puzzles about dark energy, cosmic acceleration, and the nature of spacetime itself. The quantum vacuum is not empty nothingness, but rather a dynamic medium whose energy balance properties determine the structure and evolution of the cosmos.